sklearn, linear model, passive-aggressive classifier. Description: the passive-aggressive classifier is a linear model that uses an online learning algorithm to iteratively update its weights based on the misclassified instances. It's particularly suitable for large datasets where the data arrives in batches or sequentially. Inputs: X. The input features. Typically a 2D array where each row represents a data point and each column represents a feature. Y. The target labels. A 1D array corresponding to the classes of each data point in X. Outputs: the fitted classifier object, capable of making predictions on new data. The trained model's weight vector, representing the importance of each feature in the decision boundary. Steps: initialization: the model starts with initial weights, usually zeros. Iterative updates for each training sample. Prediction: the model predicts the class label based on the current weights and input features. Error calculation: if the prediction is wrong, the model calculates the error. Weight update: the weights are updated based on the error and the learning rate. The update is done in a passive-aggressive manner, meaning that the weights are only adjusted if the prediction was wrong, and the adjustment is proportional to the error. Metrics: accuracy: the proportion of correctly classified instances. Precision: the proportion of correctly predicted positive instances out of all instances predicted as positive. Recall: the proportion of correctly predicted positive instances out of all actual positive instances. F1 score: the harmonic mean of precision and recall, providing a balanced measure of performance. Visualization plots. Decision boundary: a plot visualizing the separation line or hyperplane learned by the model, showing how it distinguishes between different classes. Feature importance: a plot depicting the magnitude of the weights assigned to each feature, highlighting their relative importance in the model's decision-making process. Fine-tune parameters. See the penalty parameter, controlling the strength of the regularization. A higher C value indicates less regularization, potentially leading to overfitting. Fit intercept: whether to include an intercept term in the model. It's generally recommended to include it, as it allows for a better fit. Loss: the loss function used for training. Hinge is the default and suitable for binary classification, while squared hinge can be used for multi-class problems. Maxiter: the maximum number of iterations for the training process. Uncertainty methods. Confidence scores: the model can provide confidence scores for its predictions, indicating the likelihood of each class. This can be helpful for quantifying uncertainty and making informed decisions. Ensemble methods: combining multiple passive-aggressive classifier instances with different random initializations or hyperparameters can provide better generalization and robustness. Challenges and fixes. Challenge 1: overfitting: the model might overfit the training data, resulting in poor generalization performance on unseen data. Sample use case: when the training data is noisy or has a high dimensionality, the model might learn to perfectly classify the training data but fail to generalize to new data. Fixes. Regularization: use the C parameter to control the strength of regularization, preventing the model from becoming too complex. Feature selection: select only the most relevant features for training, reducing the dimensionality and preventing overfitting. Early stopping: monitor the model's performance on a validation set and stop training when performance starts to degrade. Challenge 2: sensitivity to outliers: the model can be sensitive to outliers in the data, which might significantly affect its decision boundary. Sample use case: in datasets with outliers, the model might be heavily influenced by these outliers, leading to incorrect predictions and a skewed decision boundary. Fixes. Data preprocessing remove or transform outliers using techniques like robust scaling or outlier removal algorithms. Robust loss functions use loss functions that are less sensitive to outliers, such as Huber loss. Ensemble methods combining multiple models can reduce the impact of outliers by averaging their predictions.